This is a circle with radius r. So far, so good. Now consider yourself standing in the same plane as this circle and looking in the direction of its origin. Now some points are visible, such as this point right here or this point right here. However, obviously some points are not visible because they are blocked by other points on the same circle. And to get an idea of which points are visible and which points are not, we are going to draw the lines of visibility, which are basically straight lines that start from where you're standing and are tangent to this circle itself. And the points where these lines touch the circle will be the boundary points of the region which we can actually see. So we will call this region S. And the puzzle that we're going to solve now is, given this angle alpha, the angle between the two lines of visibility, what is the proportion of the circumference of the circle, or the percentage, that we can actually see? Intuitively, we see that if we come closer to the circle, this angle alpha will increase, but the proportion that we will be able to see will decrease. This region S will decrease. However, vice versa, if we step away from the circle, this angle alpha will decrease, but the proportion that we will be able to see from the circumference will actually increase. And let's now put this intuition into a mathematical formula. The first thing that we need to realize is that the proportion or the percentage that we can see from the circumference of this circle is simply the length of S divided by the total length of this circle, or the circumference of this circle, which we will call capital C. So the ratio or the percentage of visibility is equal to the fraction S divided by C. And of course, we know the circumference of a circle is simply given by 2 times pi times the radius r. So this of course leaves us with how to determine this S. How can we write this S as a function of our angle alpha? And to do this, let's remind ourselves that S is an arc length, and therefore it can be written in a different way. Let's draw 2 lines in our circle connecting its origin to each of the boundary points that define this arc length S. And note that these are also the points where our lines of visibility touch the circle. These new lines will define another angle, which we call beta. And having defined this beta, we can now use it in the formula that allows us to rewrite the arc length S as the product of this angle beta and the radius r. So now that we have found a formula to rewrite this arc length S, we can plug it into our equation for this ratio that we are still looking for. We find that it is equal to beta times r in the numerator divided by 2 pi r in the denominator. Now clearly this r drops out, so this ratio is not dependent on how large the circle is. And we see that we get that the ratio of points that we can see compared to the entire circle is this angle beta divided by 2 pi. And before we go on, let me note that this 2 pi is actually also an angle. It's simply 360 degrees written in units of radians. And if you want to get a quick recap on this conversion between radians and angles, let me just point you to the short video I made where I covered this conversion in detail. In the end, we find that the ratio that we're looking for is equal to this angle beta divided by 360 degrees. However, we're not done yet, because we found our solution as a function of beta, but we wanted it as a function of this other angle, alpha. So what we still need to do is how to rewrite this angle beta as a function of our original angle alpha, which is what we will do right now. To connect these two angles, let's use our knowledge on triangles. Now, before we do so, of course, we need to find an appropriate triangle that involves both alpha and beta. And a very evident way to get a triangle in our geometry figure is to connect these 2 points, the point from which we are looking and the origin of our circle. Now let's look at the 3 angles of our triangle. We note that this line exactly splits alpha and beta in 2. So we get the first angle being alpha divided by 2, and the second angle will be beta divided by 2. And taking into account that this light blue line is a tangent line and this green line is a normal line, and we have constructed them in this way, we know that this angle will be a right angle, or 90 degrees. So having defined this specific angle, we can use our knowledge on triangles. we know that the sum of all of the angles inside of this triangle is equal to 180 degrees. Now this will be of course 90 degrees plus alpha divided by 2 plus beta divided by 2. And if we write it in different colors, just to show that both alpha and beta are involved in this equation, we get 90 degrees plus alpha divided by 2 plus beta divided by 2. And we see clearly now that we have a formula which involves both alpha and beta. So we can use this equation to write beta as a function of alpha. Rewriting it, we get 180 degrees minus 90 degrees is equal to 1/2 times alpha plus beta. Or if we bring this 1/2 to the other side of the equation, we get 180 degrees is equal to the sum of alpha and beta. And this can be very easily be rewritten as beta being equal to 180 degrees minus alpha. And this is exactly what we were looking for, because now we can rewrite the formula that we found for the ratio that we were looking for by replacing beta with what we just found. So in the end, we get that the ratio of points that we can see compared to the entire circumference of the circle is equal to 180 degrees minus alpha divided by 360 degrees. And we can split the numerator to find that the last result will be 1/2 minus alpha divided by 360 degrees. And as a last check, we can see if our mathematical formula that we found is in correspondence with our initial intuition. Therefore, we are going to look at some extremes. First, alpha is equal to 180 degrees. When we see that this is exactly at the surface of our circle, we find that the proportion is equal to 1/2 minus 180 degrees divided by 360 degrees, which is 1/2 minus 1/2, which is exactly 0. And this makes sense. If you're standing at the surface of our circle, then you can basically only see one point out of all of the possible points of the circumference. And if you then involve some continuities, then, well, basically 0 makes intuitive sense. The second extreme scenario is when alpha is equal to 0, or this is when you go infinitely far away from the circle. Then we simply get that the ratio is equal to 1/2 minus 0 divided by 360 degrees, which is of course 1/2. And this makes sense because the farther away you go, the more you can see of the circle, but of course it makes sense that you cannot at one point see the entirety of the circle. The best you can do is to only see 1/2 of it. Now you probably notice that this is all in 2 dimensions. It's actually a 2-dimensional version of a much harder 3-dimensional problem, on which I've made a dedicated video. So if you want to take on the challenge and step it up a bit, then I invite you to check out this video, where we are looking at a satellite, which is looking at the Earth, which is a sphere instead of a circle, and it basically asks the same question. Depending on the height of the satellite, what percentage of the Earth's surface does it actually see? And I warn you, this is quite a difficult problem. And with that, I thank you for watching, and I will see you in the next one. Bye.